Hello, I welcome you all in this presentation related with the subject materials processing, fundamentals and practical. And we are talking about the welding of metals. So, in the last presentation I talked about the solid state joining process and their principles. In this presentation I will be talking about the two types of processes related to the solid state joining and then resistance welding process. So, wherein heat is generated by the electrical resistance heating or Joule heating principle and the maximum heat is generated at the interface, so that the localized melting at the interface is facilitated for development of the joint. Okay. So, as far as the content is concerned, in solid state joining process category, we will be talking about the diffusion bonding and then roll bonding first, and thereafter principle of the resistance spot welding and the relevant the steps and process parameters that control and govern the joint quality. Okay. So, as far as the diffusion bonding is concerned, this is a solid state joining process where there is no melting. So, this process heavily relies primarily on the diffusion for development of the bond at the interface. So, since the things remain in the solid state and the diffusion process depends heavily on the diffusion. So, it is very important that the surfaces, which are in fact all real surfaces, have the peaks and valleys at the surface. So, and apart from that, lot of impurities are present at the surfaces of the components to be joined. Okay. These impurities may be in form of like absorbed gases, okay, and these may be in form of the compounds of these gases like oxides and nitrites. There may be a deformed layer also at the surface and unaffected base metal below that. Okay. So, when we have adsorbed gases and the oxides present at the surface, these effectively, and that too these are present on both the sides, both the surfaces of the component to be joined. Even if we put them together, these layers, these impurities which are present at the surface will hinder or resist the flow of the atoms from one side to another. So, they will resist the diffusion, basically movement of atoms across the interface, and thereby our the diffusion bonding process will be compromised, or that will be very adversely affected. So, there are few, therefore, there are few requisites as far as diffusion bonding is concerned. What is that? Surface roughness must be very low. So, efforts are made like surface roughness Ra is like say 0.1 micrometer. So, that when the two surfaces are brought in contact with each other, there is reasonably good metal to metal contact at the interface when the surface roughness is low. This is one. The second, the metal to metal contact can be there only if the impurities are absent. There is no adsorbed gases, no oxides and other impurities present. Therefore, apart from the good surface finish, by reducing the roughness, the surface cleaning is another crucial step in diffusion bonding. So, for that we can use mechanical cleaning first, like use of the wire brushes or the emery paper, and then we can also go for chemical cleaning and ultrasonic cleaning. Okay. So, these will help to remove the chemical compounds, organic compounds, if these are present on the surface of the components to be joined. So, once we have realized the very good surface finish and the impurities present on the surface have been removed, then on putting the components to in contact with each other under pressure, what will happen? They will come in very close contact with each other, and when the conditions are made favorable, then diffusion across the interface can start. Okay. So, the two components are in perfect metal to metal contact, and to realize that, what we do, we also apply external pressure. Say one component is fixed, another one, and load is applied through the another one. So, when the load is applied, what will be happening? Even despite of realizing very low roughness and very low and very high surface finish, still few peaks and valleys will be there. So, under pressure it is expected that these peaks and valleys, okay, these will collapse, and when these collapse, so they will be deforming like this at the interface. But certainly this kind of the collapsing of the peaks and valleys under the externally applied pressure will be increasing the metal to metal contact. Okay. So, that will in turn facilitate later on the diffusion. Okay. Additionally, one more thing will happen, like when the metal to metal contact has been established, the diffusion will not be fast or good enough to develop the joint, because what we need, the diffusion of the atoms across the interface, and that heavily depends on the temperature. So, what we do, the components are placed in a controlled chamber, okay, which is at high temperature. So, high temperature chamber, what it will be doing, increasing the temperature of the component and temperature. So, the interface temperature will also be enhanced, and that in turn will facilitate the, that will increase the diffusivity or the diffusion coefficient to facilitate the movement of atom from one side to another. So, on increasing the temperature, what happens, our yield strength is reduced and ductility is enhanced. So, when the reduction in yield strength and ductility takes place, under the pressure, the peaks and valleys will further get collapsed, okay, and the collapsing of the peaks and valleys of the softened material surfaces will further enhance the metal to metal contact. Additionally, at a high temperature, when the pressure is maintained for longer time, even creep will occur at these peaks and valleys, and that will further help in increasing the metal to metal contact. Once the good metal to metal contact has been established, then what we will be looking for is this, that the favorable conditions of a high temperature in a vacuum controlled furnace, high temperature furnace in which components have been kept under pressure. Okay. What we want, that there is no atmospheric air or the gases, absence of air. Okay. So, what we do, we use the vacuum pump to take out all this air. Okay. So, when we take out, certainly the vacuum will be created. So, when vacuum is created, we so this chamber will be free from any kind of the oxygen, nitrogen and hydrogen. So, on heating, when the heating is done in vacuum where there is no oxygen, nitrogen or hydrogen, it will keep the surfaces clean, and they will not be affected due to the interaction of the metal with anything else, because there is no the other kind of the gas which can form some kind of the compound at the interface and resist or interfere with the diffusion. Okay. And that is why heating of the component at high temperature must be done for the diffusion bonding in vacuum condition. So, vacuum, depending upon the affinity of the metal with the atmospheric gases, we can use the vacuum from 10 to the power 3 minus 3 to 10 to the power minus 7 torr. Greater the reactivity of the metal with the atmospheric gases, higher will be the requirement of the vacuum to avoid any kind of the impurity formation at the interacting surfaces, which can interfere or hinder the diffusion across the interface. So, that is how we have the temperature is one parameter, because it decides how fast the diffusion will be taking place across the interface, because that affects the diffusivity and diffusion coefficient. And since the diffusion is a temperature and time based phenomena, longer the time is given, greater will be the diffusion across the interface and better will be the bond. So, the time is the another phenomena, another process parameter. Then the pressure is the third one. If we apply lesser pressure, then the collapsing of the peaks and valleys at the interface will be limited, metallic bonding will be limited in the initial stages, and later on, if we increase the pressure, the metal to metal bond, due to the increased collapsing of the peaks and valleys, increased localized surface layer deformation, increased creep behavior of the near surface layers. What will happen? Our the metal to metal contact will enhance, and that in turn will facilitate the diffusion across the interface, will facilitate in the development of the sound and good joint. Okay. So, the vacuum in pressure, time and temperature, these are the say 4 parameters about which we have talked. Sometimes what happens, if we are not in position to realize very low surface finish, okay, like this. So, the surfaces are having the irregularities both the sides, and we are not in position to realize very low surface roughness and very good surface finish. Then what we do, sometimes we use the interlayer which is made of the very soft and thin layer and of the material which is compatible with the both the components. If it is same metal joining A and A, then the interlayer being placed between the two components which are to be joined, this interlayer should be compatible with the parent metal, and if it is A and B, in case of the dissimilar metal joining, the interlayer must be compatible with both. This is the second requirement. So, the first is it should be soft and thin, okay, and then compatibility with the parent metals. So, that if in the case of same metal, it should be compatible with the parent metal. If it is dissimilar metal, the joining by the diffusion bonding, then interlayer must be compatible with both the parent metals. So, what happens, these irregularities which are present at the surface, and when we put the interlayer at the in the gap between the two components at the interface and under the pressure, what happens, this interlayer deforms easily because it is soft, it is thin. So, it fills the ups and downs, peaks and valleys which are present at the surface. So, this filling helps in reducing the gaps and voids at the interface. So, our aerial gaps are eliminated by the interlayer, and that in turn helps in improving the metal to metal contact. So, whenever interlayer is used, it facilitates the diffusion, it reduces the time required for diffusion bonding because of the increased metal to metal contact during the bonding. So, what happens, there are certain stages in the diffusion bonding, about that we can see here. Initially the two surfaces, metal A and metal B, okay, and you can see there are a lot of peaks and valleys at the surfaces, that is what we can see, and these are, and apart from that there are a lot of impurities present in form of surface oxides and moisture. Okay. So, first job is to take care of these surface impurities which are present, and also efforts need to be made for reducing the ups and downs, peaks and valleys present at the surface. Say when these two components are brought together, okay, under pressure, these will get collapsed. Okay. When these will collapse, there will be metal to metal contact will be established at many places, but still you will see that there are a lot of gaps are left. So, this collapsing or yielding of the surface irregularities will improve the metal to metal bonding, but still if you have the impurities or the aerial gaps or the voids at the interface, the diffusion will not be there. Once everything, all the peaks and valleys have collapsed and good metal to metal contact across the interface has been established, the diffusion will take place from one side to another. So, once this stage is established where there is no surface impurities and the yielding has resulted perfect metal to metal contact, diffusion across the interface will facilitate the development of the metallurgical bond, and that is what we can see here. Near surface layers, there is a possibility due to the localized plastic deformation, a strained and a refined zone at the interface will be formed, and then there will be formation of the new grains also because of the recrystallization. So, we may not be able to distinguish like where is the interface if the diffusion bond has been developed. So, if we try to see the effect of the pressure. So, increasing when we use the lesser pressure and load carrying capacity or joint strength, okay, joint strength. So, when you use the less pressure, due to the less, when we use less pressure, there will be lot of interfacial voids, and that will reduce the metal to metal contact, and therefore, our joint strength will be limited. But if we increase the pressure, our joint strength will enhance due to the increased the metallic bonding, increased diffusion across the interface, so improved joint characteristics. So, there will be a limit there, later on it will start getting flattened once the 100% metal to metal contact has been established. This is about the effect of. So, here in the beginning more voids at the interface, somewhat lesser voids at the interface, and almost nil voids when the pressure is high. But this pressure can affect or can deform the bulk, the weak material also in dissimilar metal combination. So, we have to choose the pressure in such a way there is no deformation or unnecessary the yielding of the permanent yielding of the components which are being joined by the diffusion bonding. So, this is one effect of one parameter, like say if we take the temperature. Okay. So, when the temperature is less, certainly, so in here we have joint strength. Okay. So, when we work with the lesser temperature, lesser bonding temperature, it for a given time it will be resulting in the weak bond, because there the diffusion coefficient will be less, and it will take very long time to develop the good diffusion bond which is free from the defect. So, for lesser temperature, lower temperatures, it will result the bond, but with lot of voids. Okay, more voids, okay, at the interface. If the temperature is increased, diffusion coefficient will increase, and that will in turn will help in reducing the interfacial voids, and further higher temperature it will further eliminate the voids at the interface. But further higher temperature, what it can cause? It can start the thermal degradation of the material itself. Because of the overheating, substrate material may starts getting degraded due to the overheating. So, initially there will be increase in joint strength, but when we go for overheating beyond the optimum value, thermal degradation of the parent material itself starts. So, here joint may be good, but the base material or the parent material itself starts degrading, okay, due to the overheating. If we talk of the time also, so here in x axis for a given diffusion bonding temperature, for a diffusion bonding pressure. So, here we have the joint strength. Okay. For short time, certainly there will be more voids, so lesser strength, increasing the time will be reducing the interfacial voids, increasing the joint strength. Again we will have the optimum thing, and then our joint strength will start decreasing, because overheating means keeping the components at a higher temperature for long, it will start grain growth and other thermal degradation or metallurgical degradation due to the high temperature exposure for long time will start degrading the joint performance. Okay. So, this is about our the effect of the process parameters. Likewise, if we see under the for a given temperature, pressure and time, if we try to study the effect of the vacuum, low vacuum or high vacuum. Okay. So, in case of the low vacuum, there will be lot of the atmospheric gases present in the vacuum chamber, and that can interact with the material at the interface, and these oxides and impurities will resist the diffusion across the interface, and therefore, there will be more voids when the low vacuum is used, and the reduced diffusion coefficient, reduced diffusion of the atom across the interface will result in the significant voids at the interface. But when we use high vacuum under the identical temperature, pressure and time conditions, we will have the higher joint strength, because perfect metal to metal contact in absence of any kind of the impurity will facilitate the higher joint strength. Okay. So, this is how we can see the effect of various process parameters. Now, as far as the roll bonding is concerned, roll bonding is another solid state joining process, which is particularly used for the development of the cladding and for development of the like composite material layers. Okay. So, in that case what we do, this is the substrate, and over this if you want to apply a layer of one material like both the sides, say this is mild steel, and if you want to apply layer of copper both the sides, then we can use the roll bonding. So, the one application is the cladding, another one is where we want to develop the composite layer. So, we use the layers of the different materials like this is one layer, okay, then we use the another layer, okay, like this, another, then this layer, and then the another layer. Okay. Now, the set of these 4 sheets will be passed through the rollers. So, these will be rolled. So, during the rolling things will be compressed, there will be great reduction in thickness, reduction will take place. When the significant reduction in thickness takes place, these sheets will be bonding with each other. Okay. Once these get bonded, so the reduction may be like 30 to 40% of the thickness, okay, of the total accumulated thickness. Once this is rolled, what we will be doing? We will be cutting them again, and again these will be stacked together and passed through the rollers. So, this kind of the approach is used for development of the materials by mixing 2 or more kind of the thin material sheets. Okay. So, the process involves the micro plastic deformation at the interface, but actually it is macro plastic deformation as far as the layers are concerned. Like if we start with 5 mm, 5 mm, and then after rolling, like say, so the bond will be developed like this, reduced to say 6 mm after rolling. So, here what will happen? The reduction in thickness is macro level, but the interfacial deformation is micro level. Okay, micro level plastic deformation at the interface. So, what is important for this bonding? Okay, that is important to be seen. So, obviously, since we are just rolling the things by putting or stacking the sheets together, so there must be very good metal to metal contact between the 2 sheets, and for that what is necessary? Very good cleaning, free from impurities. Okay. So, surface roughness of the sheets coupled with the cleaning, that will ensure the good metal to metal contact, especially when these are rolled. So, the extremely good cleaning is a prerequisite for the roll bonding, so that they come in metal to metal contact when the components are being rolled. Okay. That is one. And when you see that the 2 components, when these roll, they come very close to each other, and that in turn helps in development of the bond. So, how the bond is developed? Like say when the rolling happens, there will be certainly some kind of the heat generation. Okay. If the rolling speed is less, the heat generated, whatever heat will be generated, that will remain at the interface, but there will be more bonding time, like 2 sheets will be there under pressure for longer time when we use the lesser rolling speed. So, rolling speed affects the 2 things. One is the bonding time, means the time for which the pressure is maintained. Higher the speed of rolling, lesser will be the time for which the sheets will be there together. On the other hand, like say the heat generation will be affected also with the rolling speed. So, if the rolling is being, so rolling we can do in 3 conditions. One is the room temperature condition, then it will be termed as the cold roll bonding. Okay. And if it is little greater than the room temperature, then warm kind of thing, and otherwise hot roll bonding. Okay. So, depending, this classification is based on the temperature at which the rolling is done. We know that when the rolling is done at a higher temperature, if the temperature is high, then the diffusion across the interface will be very fast, it will be very good. Okay. And the bond across the interface, that will be formed very quickly, and that will be formed due to the recrystallization, fast recrystallization, we can say dynamic recrystallization when the hot rolling is carried out. Otherwise, at room temperature, what will happen? Impurities, irregularities which are present on both the sides, these will get collapsed. Okay. And once these get collapsed, they will be interlocking with each other. Apart from that, some diffusion across the interface, when the things come in metal to metal contact with each other, will also help in development of the bond. So, as far as the important parameters are concerned related with this roll bonding process, the thickness reduction, thickness reduction. So, there should be minimum threshold reduction, which is usually like say 30 to 50% depending upon the metal, type of the metal and the surface condition. Okay. So, once this great thickness reduction is achieved, then the bonding between the two sheets across the interface will be extremely good. Rolling speed, it is another factor because it affects the time for which the two sheets remain in under pressure during the rolling, and it also affects the rate of the heat being generated and transferred to the material which is being rolled. The rolling temperature is another one. Higher rolling temperature facilitates the roll bonding because metal becomes soft, of lower yield strength and greater ductility. At the same time, diffusion across the interface is also facilitated when the rolling temperature is high. Surface conditions certainly affects the things significantly, especially at the interface. Why? Because if the surface is clean, free from the impurities, then it will be facilitating the easy diffusion across the interface for the development of the roll bonds. Okay. As far as the resistance is spot welding, this is the another kind of the process. So, in this process is based on the Joule heating. What is that? Like say we have the two sheets to be joined. Primarily this process is used for the development of lap joints. So, we have one electrode usually made of copper and another electrode on opposite side is placed like this. This is also made of copper. So, current is supplied, say current I is flowing and the electrode will be applying pressure onto the sheets to be joined, so that they remain firm in contact with each other. So, metal to metal contact between the sheets to be joined is crucial and that is maintained through the application of the pressure. So, the role of pressure is primarily to ensure the metal to metal contact and also ensure that the solidification of the molten metal, whatever is created at the interface, that happens under pressure. Okay. So, the pressure is one thing, the flow of current across the interface is the another aspect, and the how long current is allowed to flow, that is the third aspect. So, the pressure, current and the time of the current flow, these are the three important parameters. Apart from that, we can say surface condition, like the surface condition will be determining the contact resistance at the interface. If lot of impurities are present, then resistance will be high. If the surfaces are clean, impurity and the surface is very smooth, then contact resistance will be less. So, R contact resistance at the interface, that is the another factor. Okay. So, what happens when the heat is supplied, current is supplied across the interface? So, say current I is flowing across the interface, so it will be causing I square RT heating. So, the T is the time for which current is allowed to flow, R is the contact resistance at the interface and I is the current, that is controlled current that is allowed to flow. So, current is fed through the electrode to the components which are to be joined. When we have enough pressure, the firm metal to metal contact between the electrode and the sheets will be maintained. So, there will not be any sparking. Why? Because the current is too high, like 20,000 to 50,000 ampere current is allowed to flow. So, the current value is extremely high, while the time for which current flows is in microseconds or in milliseconds. So, the time is very less for which current will be flowing. Okay. So, high current requires that things remain in firm metal to metal contact with each other. Okay. So, if we can see the schematic of the process, these are the electrodes, the pressure is applied through the electrodes onto the components to be joined sheet A and sheet B. Okay. And here when the current flows, the maximum heat is generated at the interface, little bit heat will be generated at the other two interfaces also between the sheets and the electrodes. Since the R is maximum at the interface, so our maximum heat will also be generated at the interface and accordingly we will be getting the maximum temperature. Okay. If you see, this is the temperature and this is the variation in temperature across the interface, we can see there is a rise in temperature also between the electrode and the sheet interface. Okay, that is what we can see, but here R is less, current I is same in all the cases, in all three sections like 1, 2 and 3. So, but current I is same, but what is different is maximum at the interface and lesser at the copper electrode and sheet metal interface, both the sides. Okay. And that is why what we will see, there is a rise in temperature of the surface layers also of the component being joined. Like say this is the sheet, and if at the top surface it is getting heated, likewise the bottom surface is also getting heated, apart from the maximum heat generation at the interface. So, maximum heat generation at the interface will be causing the melting, followed by solidification under pressure will result in the weld nugget, okay, and that will ensure the metallic continuity for development of joint. But still maximum heat being lot of heat generated at the top surface and the bottom surface of the sheet, which is in contact with the electrodes, and that too under pressure, what it will cause, the electrode will try to get indent, try to penetrate the surface, and it will be causing the indentation on the top surface. So, what will be getting, basically the top surface will get indented like this on the like this, and the bottom sheet will also will get indented like this, and somewhere in the middle we will have the weld nugget like this. Okay. So, this indentation actually will be reducing the load resisting cross sectional area. Okay. This indentation is considered to be undesirable. So, to avoid this we can use multiple approaches, and like the use of the cover sheet to protect the sheets from this kind of the damage. Okay. So, what we do actually during the welding is resistance spot welding, like say the initially the pressure is applied, so that the sheets are placed between the electrodes and the pressure is applied, and that pressure is maintained throughout, okay, throughout the welding. Okay. So that when the current is allowed to flow, there is no significant spark, there is no sparking at the interface between the electrode and the workpiece. Initially we may supply little lesser current, so that the preheating happens and then main welding current is applied. Preheating is sometimes needed to avoid any kind of the weld defect formation or formation of the undesirable set of the mechanical properties and the microstructural aspects. Okay. So, the welding initially we can supply the preheating current, so that will be preheating the sheets to be joined, then main current is applied, so that the fusion at the interface is facilitated. Thereafter, the current is reduced, so followed by the solidification, then again current can be supplied for the post weld heating, so that on reheating again the desired microstructure can be realized. If we do not choose these process parameters, like I is the surface based on surface condition, T and pressure. If we do not maintain these process parameters properly, then what will happen? The issues that are commonly encountered, indentation both the sides, the presence of the defects in form of porosity and inclusions, and sharp stress concentration at the interface. This is in any case the inherent part of this kind of the joining process, where at the periphery of the spot weld high stress concentration is observed, and that in turn reduces the fatigue strength significantly. Okay. So, as far as the joint strength of the resistance spot weld joint is concerned, the weld nugget diameter, like say these are the sheets, and if the nugget diameter is small, then this is the zone where we have metallic continuity. So, this area will be determining if we have the shear strength Fs and this area is A1, then our joint strength will be F1. Okay. If this area is increased, then for a given material Fs is fixed, then our A1 will become A2 and our F2 will be Fs multiplied by A2. A2 will be greater. So, nugget area is the main factor in a spot weld joints that will be determining the joint strength, especially when it is sound. Now, I will summarize this presentation. In this presentation, basically I have talked about the two types of the solid state joining processes, namely the diffusion bonding and mechanism of the diffusion bonding and the various process parameters related with the diffusion bonding. Then I also have talked about the roll bonding, the application of the roll bonding and various the process parameters associated with the roll bonding. I have also tried to introduce the resistance welding process and the principle on which this spot welding process works along with the important process parameters. Thank you for your attention.